was my friend had a birthday party that, but from tomorrow it will be the regular time. I mean the other days. Okay, so we're good to go, and I hope you guys have solved this in enough time. From tomorrow onwards, I'm gonna create, um, an assignment that you need to put your papers in. Okay, so that I know that you guys are doing that. Okay. So now let's have a
We
look.
have to upload this paper.
Yes, definitely.
Okay.
And while I'm doing this, it's a good habit that you correct your work. Okay. And when you correct your work, you can go back. You already know which part of the syllabus you don't understand fully. So you can review the videos, you can also review the notes, and even still you don't understand something, you can always ask me. But this is why past paper session is important. Like you don't have to solve bulk, you have to create quality, okay, in your work. So I expect you guys to just do not copy it from the mark scheme. Just wait till I do it, and then you can fix it. Anyway, so let's begin. I just need to check quickly what's happening everywhere. Okay. So going on to the part. Okay. So the first thing that we're going to look at is the Newton law of gravitation. In Newton's law of gravitation, you just need to write, like for 2 marks, like I always say, that force of attraction is proportional to product of masses and between two bodies, and inversely proportional to the square of their separation. Okay, so that's what you're going to write. Now it says use Newton's, show that this gravitation field strength is this. So F is equal to G M over R square, and also F is equal to mg, which is the force. So you can put mg, and then you can just put G M over R square. M and M will cancel out, so G will be G M over R square. So that would be it. Pretty simple. And then it says the Earth has a mass of this, and radius of this, and Moon is this, blah 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 blah. And show that the gravitation field strength at the surface of Moon due to the mass of the Moon is this. So you just need to use the formula on top. That would be G equals to 6.67 times 10 raised to minus 11. And mass of Moon is given as 7.35 times 10 raised to 22. And then you got to, because we're talking about the surface, so you got to put the radius, which is 1.74 times 10 raised to 6 and the whole square. And I believe it should give you the same answer. So 1.74 times 10 raised to power 6. And I hope it was in meters. Yes, it is in meters. And squared. Oh, and squared. So I'm getting exactly 1.62 newtons per kg. So proved. And then going to the next. Explain why there is a point x on the line between the centers of Earth and the Moon, where the resultant gravitational field strength due to Earth and Moon is zero. So about this, you guys need to understand that first of all, if I were you, I would write the gravitational field strength is a vector quantity. Okay, so equal magnitude and opposite forces. If you write this will give you 2 marks. Opposite forces, sorry, opposite direction. Okay, opposite direction will cause net effect to be 0. So that's what you were talking about, null point actually. Then if you have any questions there, please let me know.
Sir,
Then
could you explain that part once again?
what I'm saying is, if this is Earth and this is Moon, so there will be some point in the middle, somewhere between them, not in the middle exactly, where the gravitational field strength of Earth and gravitational field strength of Moon will have the same value, and they will have opposite directions. And because they're vector quantities, so when you add them up, they're gonna give you a net um, gravitational field strength of force to be 0. Okay.
Okay, sir.
So then he asks about the distance x. So if I were you, I would obviously create a diagram. Creating diagrams help you figure out what you're basically looking at. So I'm looking at this x point, or let's call this null point, okay, n. So if I'm not wrong, they gave us the distance between them, and they said the Earth and Moon can be, and their centers are distance of 3.84 times 10 raised to 8, which means from here till here, it is 3.84 times 10 raised to 8 meters. What do I need? I need to find this distance x from the moon. So I'm going to say this distance is x. If this is x, then this distance from here to here would be this 3.84 times 10 raised to 8 minus x. You guys agree?
Yes, sir.
Yes.
And in the previous part, we've learned that at null point, the gravitational field strength of moon is equal to gravitational field strength of earth. So we're going to just put the values. So gm over r squared equals to gm over r squared. This is for moon. This is for earth, a moon and earth. Okay. So g and g cancels out, really doesn't matter. Moon has a mass of, I think, 7.35 into 10 raised to 22. 7.35 times 10 raised to 22 divided by the distance from moon to the null point is x squared, and then earth was 5.98 times 10 raised to 24, and then divided by the distance was 3.84 times 10 raised to 8 minus x whole square. Now typically what you want to do is, because this will make a quadratic equation, so you better take under root on both sides. Taking under root on both sides help you tremendously, because by doing that, basically what happens is that you get to remove the squares on the variables. So you get 7.35 times 10 raised to 22 under root over x equals to 5.98 times 10 raised to 24 under root over 3.84 times 10 raised to 8 minus x. So then, I don't know, um, it's better to cross multiply this, and if I cross multiply, it will be 3.84 times 10 raised to 8 minus x over x equals to 5.98 times 10 raised to 24 divided by under root 3.35, 7.35 times 10 raised to 22. Okay, so you can divide x. This will be 3.84 times 10 raised to 8 divided by x. This will be 1, because x divided by x will be just 1. And you can basically find this. So let's do that. Okay, so this is going to be, okay, I'm going to solve this in a better way, like this. 5.98 times 10 raised, oh my goodness, 10 raised to power 24 and divided by 7.35 times 10 raised to power 22. Okay, this comes out to be 9.02, and you add x here, so it's going to be 3.84 times 10 raised to 8. Add 1, it will be 10, so 10.02 times x, and then you could divide, this whole thing, and then just divide by 10.02. So I'm getting something like x to be 3.83 times 10 raised to 7. So I'm just gonna write 3.83 times 10 raised to 7. Now it's good because the least value we had was like 3 significant figure. So generally it's a good idea to give the least significant figure or one more than that, but you should not give less or bigger than this value. Okay, so just do that. So 2 or 3 is fine. Anyway, so I'm going to go to the next. If you have any questions, do let me know. Okay. So then, part 2. It seems like electric field question. Okay, no magnetic field, electric field. I don't know. So there's a sphere, and there's a sphere of mass and charge, and the sphere is a uniform electric field vertically upwards. Vertically upwards means that has to be positive side. This is a negative. That's how it goes. And the plane in which the sphere moves, that's 90 degrees. Okay. Now it says there's a magnetic field as well, and it goes in a circle, and this electric field out of the page. Okay, so viewing it from the top, right? Okay, and there's a magnetic field as well. Pretty good. So determine the direction of magnetic field. Now, if you look at the movement of sphere, right? So the movement of sphere is going at a certain angle like this, right? So what I'm going to do is I'm going to make the velocity vector. And if I make the velocity vector, I can clearly see that the sphere is going here. The velocity changes from here to here, which means the force on this should be here. Now I'm going to use my left hand rule. And then this should be your thumb. Sorry, thumb should be this one. Middle finger upwards. So it's basically, what do we need to do? Direction of magnetic field. Wait, so thumb up. Wait, thumb is here. And this is a positive charge, right? I'm not wrong. This is a positive charge, yes. Okay. So left hand thumb, velocity, and direction of magnetic field. So direction of magnetic field seems like this one, right? So which is this is view from above. So it is like downwards. If you look at this will be like downwards then. Okay, because if view from above, then obviously it is like going down against it. So I'm going to write downwards here. Okay, please do not
So
write
I said into the page. Is that fine?
into the page with respect to figure 2.2. If you write this, I think they will accept it. But because they've given you above, so you should write downwards then. Okay. Then says why the motion of sphere in the horizontal plane is because this is a horizontal plane, so vertically it has to go down. So why the motion is horizontal plane? This. So first of all, we would say that obviously whenever magnetic field is perpendicular to the motion. Okay. Then what happens is that centripetal force is provided by the magnetic force. All right, so you just need to remember that. Magnetic force, and you can add that magnetic force that's 90 degrees to the velocity. That is a good habit of writing like that. Okay. Then says calculate the strength of uniform electric field. Well, that's not bad. If it's kept horizontal, like if it's kept horizontal, so it means that the weight of the sphere must be acting down and the electric field must be putting force like this. Electric field can be found out F equals to EQ, okay? And weight is mg because it's an equilibrium vertically. So we can say then the electric field is equal to the weight. And if that is the case, then EQ equals to mg. Okay, and what do we need to find? Strength, we need E. So mass was given, I think, here 1.6 times 10 is to minus 10. G is 9.81 divided by charge was also given 0.27 nano. 0.27 nano is 10 raised to the power minus 9, I think. Okay, so I don't know what the answer is. Calculate it. Okay, multiply by 9.81 and then divided by 0.27 divided by 10 raised to power minus 9. So that's 5.81. That should be your answer. Anyway, by considering the magnetic force on the sphere, show that the flux density of the uniform magnetic. So we want to find B. Okay, now. It's pretty simple. Whenever you see something going in circles, right? So we got the radius and we got the mass. It means that the magnetic field must be in the centripetal, like providing centripetal force. We have already written that as well. So BQV equals to mv squared over r. You can cancel this. You can also use mv over bq. You already know this. So we need b, right? So we'll switch it like here. So the mass was 1.6 times 10 to the minus 10. The velocity, we don't know the velocity. That's not fair. Do you have the velocity? Yes, 0.78. Okay, very good. 0.78 divided by 3.4, I believe, and the charge was 0.27 times is to minus 9. Okay, let's try this. Minus 10 times 0.78 divided by 3.4 times 0.27 times 10 raised to power minus 9. So that's going to be 0.136, which is 0.14. Okay, shown. Tesla. Okay. Any questions, please let me know. Okay, so going to the next. So ideal gas question. Fixed mass of an ideal gas is initially at this. So the moment you see this, you got to understand it. You got to convert this. You convert this 273 plus this will be 300 kelvins, right? Is it a 390 or 290? I think it's 290, right? It's 290 kelvins. And the gas is the volume of this and the pressure all. So what is meant by an ideal gas? So you already know that ideal gas is a gas that follows gas laws. PV is proportional to the temperature, and then you got to explain. P is the pressure, V is the volume, and T is the thermodynamic temperature. Okay, you can also write temperature in Kelvin. You can get away with that. That's fine. Anyway, so you want to find moles, and the best equation for that would be nRT. You got the pressure, 1.2 times 10 raised to 5. Luckily, our volume is also in meter cube. And this is 8.31, by the way. If you don't know, you can always go back. It's here, I think, somewhere. I don't know. Where is it? You tell me. It's not there? That's not fair.
इधर है sir.
So 8.31
For
molar
that gas
in the
constant.
data. In the
Oh,
data.
yes.
Stereo.
Yes, okay, that's good. Chalo, that's good. So that means that we're happy about it. And then the temperature, you got to take it in 290 because it has to be in Kelvin. Do not make this mistake, please. So I don't know what's next. So 1.2 times 10 raised to power 5, and then multiply by 0.25 to 4 divided by 8.31 and 290. Okay, so that's going to be almost 12 moles, right? Pretty good. And then this question is my favorite because this is the easiest. And it says the initial state represented the gas is cooled at constant pressure to B. Okay. From A to B, it was cooled and this much energy was used. The gas is then heated to volume C. Fine. The gas finally expands at constant temperature back to its original pressure volume at point A. So that's this. And the gas does work. Okay, fine. So that the magnitude of work done is this much. So work done is basically pressure times change in volume. So this formula should be very important. So it was 1.2 times 10 raised to 5, I believe. And yeah, and then change in volume. So we're gonna read off from the graph that is given. So volume changed in this section, right? So what section is he talking about? AB. Okay. And this section reads off like 0.24 and 0.08. How cool is that? They've given us, and check this if it's in VT cube, which is good. And this was 10 raised to 5, right? Yeah, and the pressure was 1.2. Okay, it was supposed to be taken from here. So we're going to change this and 0.24 minus 0.08. 0.24 minus 0.08. And then just simply do this. Oh. Okay, so that's 1920. So that means 1.92 times 10 kilojoules. Okay, proved. Pretty easy. And now come to the table, which is extremely easy. So A to B, we have already found the work done, which is 1.92. And when you subtract this, like basically the equation is the increase in internal energy is the heat plus the work done, right? So you got to add it. When you add it, so it's going to be 1.92. And with the signs, please. So
It's 19.
Sorry?
It's 19.2, not 1.2.
It's 19.2. Oh, yes. Sorry. My bad. That's supposed to be 19.2. Okay. 19.2 minus 48. So that's going to be minus 28.8. Okay. So that should be your answer. And then we have no values here. And CA, they have given thermal. What? That's not fair. Okay. Then what is happening at BC? They haven't given anything about BC, right? They've just said gas is heated. But they say finally the gas expands its constant temperature back to original pressure and volume, and during this expansion, gas does this much work. If you look at this is like expanding. Whenever gas expands, right? So it's basically doing work against, against the system is doing work, right? So it has to be negative, I think. So we're gonna put. They've already done that. There has to be something else here. What are we missing here? There has to be something, some other thing. The gas is cooled at this, and then for BC there was no work done because volume was same. So we'll do BC first. Let's just put it 0 here. And then what else is left? What else is there that we got to understand? There got to be something that is not fair with us. Okay. This was 19.2, and this is like increase in internal energy. And when it would have gotten back to the internal energy, it means that when it goes from B to C and back to A to B, B to C, so it's a closed system, which means that the internal energy must be here as the increase. When it back A to A, the internal energy should be 0. because it has reached the same point. And now we can find what happened. How can internal energy be 0 at this point? If you add it up, you must add 28.8 here. So you must have gained this much energy, right? So then it means that to do that, we're going to use the equation again to 28.8, and the heat was Q and this was 0. So it is 28.8 as well. And finally, the last one, you're going to do the same thing. Change in U was 0. Q we want to find. Work done was basically 31.6 in the negative. So it goes there. It has to be positive then. That only makes sense. Do you guys understand what I've done?
Yes, sir.
Okay. So just if those who have got it wrong, just remember that this is when you go from one point and back to the same point, the change in internal energy is always 0. Just remember that in a closed shape. Okay then. Then we're going to go to the next, which is the pendulum question. Pretty easy. They've given us acceleration versus, we're going to check the units first, and then we're going to go forward. So it says, state how the motion of the pendulum states that it is simple harmonic. Okay, so first point should be that it's basically a straight line from origin, which basically shows that acceleration is directly proportional to displacement. And then the other thing is that it has a negative gradient. Negative gradient means that acceleration and displacement are always in opposite directions. So that's basically the definition of simple harmonic motion. And then it says determine the angular frequency, which is pretty easy. What you want to do is you just need to find the gradient of this graph. How to do that? Just take the endpoints, any endpoints like this and this. And this will be, I think, 0.05 negative, and that's going to be 0.4, right? And then use the formula A equals to minus omega squared x. So you know that the gradient of that is going to be minus omega squared x. The gradient will be 4 minus 0 and minus 0.05 minus 0. Okay, 0.4 minus 0 divided by minus 0.05 minus 0. Okay, so minus will cancel out. So omega will be 0.4 divided by 0.05. Take under root and then try to find it. Under root 0.4 divided by 0.05, and that's going to be 2.83. Okay, that should be your answer. All right, then we're going to go to the next. It says the angular frequency is related to length, blah, 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 and give your answer, determine K. Fine, so we're going to square it off. And when we square it, so it's going to be omega squared equals to K over L. We already have omega value, 2.83 whole square. K and length. Length is not given. Or is it given somewhere? This is 1.24. Okay. I don't know why this question even exists. How easy it is. 2.83 times 1.24. So 2.83 squared times 1.24. And that's going to be 9.93. Okay. So, and I don't know why this basically, what would be the units? Interesting, huh? The units were radians per second, and the length was in meters. So radian square and second square and meters, what that might be, I don't know. We had to take square. It should be radian square and second minus 2 and then times meters. So radian square meter over second square. It has to be radians. What is radian squared? There's nothing, no unit I've ever seen like that. Interesting. So okay, we can write this. No worries. That should be the unit. But why would they give you? This is a value that comes from this k over L, which should be k has to be where k is the constant. Okay, fair enough. Then says when the pendulum.
Sir,
Yes.
the answer is meter per second squared.
Meters per second square.
Yeah.
Where did the radians go
Yes,
then?
sir.
So
I think
radian doesn't have any unit.
radian is a unit here. It's angular velocity. You see the unit here? I just took the units, okay? I don't know why they would give you this. Radians squared. This is very strange, you know. This should not be existing. They have said meters per second square.
Yes, sir.
That makes it acceleration, right? That makes it a,
Yes.
okay, which basically means that this is omega square should be equal to a over x then, right? Even if that is true, then x meters and meter will cancel out. A should be proportional to k, and that's true that it should be meters per second square. Maybe that's how they've done it. Not included this one. That's fine, I think. But I don't know why they would cut your marks even if you write that, because that's also correct. Because what they've done is they might have, put this whole thing when you squared it off, right? When you squared it off, they might have put it equal to a equals to omega squared x, right? So they have written it like a over x, and now a is meters per second square, x is in meters. We want to find k, and L is in meters. Meters and cancel out, so k has to be meters per second square. It's probably like that. They've done it. Okay, fair enough. No worries. Because I think, in my opinion, that if a over x is omega square, right? So it means meters per second over meters should be just radians meters per second square, and radians second minus 2 radians square. That should be the same units as these. That's why. All right, Kartika. I think that's fine. But I think it's viable as well. I don't think so. These are wrong units at all. Okay, never mind. When the pendulum is oscillating, the length of the string is increased in such a way that the total energy of oscillation remains constant. So let's explain the qualitative effect of the change of the amplitude of the oscillation. Oh, I understand. So now, if you increase the length, if you look at the formula, it is A upon X equals to K upon L, right? So if you increase the length, then it would mean that you have to increase length means you have to decrease the acceleration, right? And if you decrease the acceleration, then definitely no, you would not decrease the acceleration by that. Wait a second. Or you could do something like this. Omega square was equal to k upon L. You increase the length. You increase the length, the omega is going to decrease. And if the omega decreases, so you have to, and you have to keep something constant. You have to keep the total energy constant. So not like that. There has to be something else here. So energy is given by total energy formula is half m omega squared x naught squared. If this is constant, which basically means, and you decrease this, So you want to keep this constant, then you have to increase the amplitude here. That's how it's going to be. Okay, I got it. Let me write it down. So total energy is given by half m omega square x naught square. Okay, where x naught is the amplitude. Okay. Now what I'm going to do is, because I want this to be constant, then I can compare like energy total over x naught square equals to half m and half m omega square. Now, since omega will decrease because of the fact that we have increased the length, because length increased. So then what happens is that if you decrease this, you have to increase this because you have to keep this as constant. So amplitude must increase to keep energy constant. Is it clear, everyone? I will write this.
Yes, sir.
Okay, going to the next. So then what is rectification? Rectification is basically converting alternating current to direct current. That's what you do, direct current. Then it says what type of rectification is produced. It's a full wave rectified. Full wave rectification. All right. Then they've given you this. What is VN? VN is the voltage N. It's good. And they say blah blah blah. Use on figure, label the output terminals PQ with appropriate symbols to indicate the polarity of output voltage. Okay, so if it goes like this, and I would recommend that you take colored pens in this. Okay, now it can't go to this side, so it has to go this way, and then it can't go here, so it has to go this way, and then blah, 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 here, so it has to be positive, and then it will come here, and then it needs to go, it can't go here because higher potential. It will go here, and then here. Okay, now this here, here, and then here. Okay, so this has to be positive, this has to be negative, like that. You have to put it here. Okay, is it clear? To verify this,
Yes,
you can
sir.
use a colored pen. You take two pens, black or blue or any other color pen, and then you can take it like this way and this way. You can't go here, so you go here, and then you have to go here like this, and that confirms that you are going in the same direction, both of them. And then it says here, label both the axes with correct scales and use the space below for any working you need. So basically, originally it would be like this, okay? An AC wave would look like this. So it means this is one whole wave. And now, if you look at the formula, which is Vn equals to 6.0 sine 25 omega t. Okay, this is what it is. So it means this is V, this is V naught, this is sine omega t, like that. Is it clear, everyone? So it means omega is 225 pi, and omega is also 2 pi over t. So t will be equal to 2 pi over 25 pi. Pi and pi will cancel out. 2 over 25 is, I don't know, 0.08. 0.08 is the time period in seconds, okay? Which means this is the whole time period. This means this has to be 0.08. You guys understand this? So that means if this is 0.08, this will be 0.04, this will be 0.02, 0.06, this will be 0.10, and this will be 0.12. You guys get it?
Yes, sir.
And also, you need to make sure that the peak here got to be the voltage that's maximum, which is 6.0. So you have to put 6.0 right here. If this is 6.0, then we can put it like this. 6 and what to do? 2, 4, 6, like that, and 8. I think that would do. I think. Okay. Then we have done this, and then for 3 marks, very nice. And then we're going to go to the next. It says the output B is smoothed by adding a capacitor. The difference between the maximum and minimum values of the smooth output is 10% of the peak voltage. Oh, interesting. So it says draw the circuit symbol for capacitor showing the capacitor correctly connected into circuit on figure 5.1. So this is 5.1. You have to always connect the capacitor parallel to the output like this. And I think you have to label C. You don't have to label anything. Okay. Then on figure 5.2, sketch the variation T smooth voltage. So first of all, we need to find how much it drops, right? So to do that, to show the drop, okay, we're going to use the equation. And to do that, first of all, it was 10% drop. 10% drop means that the remaining 90% is available, right? So what is 0.9? 90% is 0.9 of the maximum voltage. So
So
it's
5.4.
5.4. So basically, it will drop from this point. So I'm going to change the color. So from this point to 5.4, I think 5.4 would be, this is 4.4, 4.8, and this is 5.2 and 5. No, I don't think so. That's correct. 4.4, 4.8, 5.2, 5.6. 5.4 we want to find. Okay, so this is like 5.2, this is 5.6. So it should be somewhere in the middle, right? So I'm going to go straight. I'm going to go straight till I write this point, and then I'm going to make a straight line like this, like that. And then I'm going to continue doing the same thing with the other points as well. Here, I think it was, yes, like this, straight lines. Uh-oh. Like this, and leave the other things because we don't have the other peaks, okay? So then it says calculate the capacitance of the capacitor. Okay, we can do that, some big deal. So V equals to V naught E minus T over RC. This is how we got to find an exponential change. So the drop was 5.4, and basically the total was this E minus the time it took. We don't know how much time it is. We're going to calculate using the graph. Uh-oh. So this would be coming down here, 0.2, and it goes till here. I think this is, if this should be 0.05, it means 52 and 0.052, 0.054, right? 0.054, I think. Chalo. Subtracted by 0.02. So the time difference is 0.054 minus 0.02. That's 0.034. Okay, so we got the time 0.034. The resistance, do we have the resistance? That is not fair. Oh, 1.2 kilo ohm. Cool. So we got 1.2. 1.2 kilo ohms is, I think, 1200. No? Yeah. Times
It
C.
is.
Yeah. So 5.4 divided by 6 equals to E minus 0.034 divided by 200 times C. Take ln on both sides. So ln 5.4 over 6.0 will be equal to minus 0.034 divided by 1200 times C. Ln E will cancel out. So then let's quickly find the values. Ln, you do this, you do 5.4 divided by 6.0, then, okay. And then you get minus 0.1054. Okay. And then minus and minus will cancel out. So C is going to be something like this. 0.034 divided by 1200 multiplied by 0.1054. And it's 0.000269. That's 1, 2, 3, 4. 2.7 times 10 raised to minus 4. I think that should be the answer. All right, everyone. Please let me know if you have still difficulty in understanding this.
Sir, the only question I have is where did you get 0.034 for the time?
I got it from the decrease. Like I know the capacitor discharge from the peak from here till this point, right? From the graph.
Yeah.
And I got the difference in time from here by reading off the graph. The tricky part about this question is if you get this wrong, you also get this wrong. So basically you lose 3 and you lose 6 marks if you get just one thing wrong. You understand?
So don't they give us C1 for using the equations at least?
Depends on the mark scheme if they've given you anything for the equation. If they haven't, then
Right, so the C1 might not always be there.
no, it's not always there.
Right. Okay.
So it's like a 6 mark loss. That is like 6%, and that's not good. Anyway, so we're going to go to the next. We're going to define what is magnetic flux. And if I'm basically, if you ever get stuck in any definition, okay, the best way to define anything is that you remember the formula. Okay, so magnetic flux was magnetic field strength times area. All right, where this area was perpendicular, if you remember, right? So I would just define this and say magnetic field strength times perpendicular area, although the definition is product of this, okay? And if you write perpendicular, I think that's fine. You get 2 marks, okay? So 1 mark for writing magnetic field times area, and it has to be perpendicular. The real definition, if you have to write, yes?
I said that number of magnetic field lines that pass through an area perpendicularly.
Number of magnetic field lines
That pass
well,
through an area perpendicularly.
well, I would not give you mark for that.
So when it comes to lines,
Okay, sir.
doesn't it become linkage?
No, linkage is when it links through a coil that has n turns.
Yeah.
Understood?
Okay.
But flux is not that. You get it? Yeah.
Right. Okay.
Sir, could you give us the model definitions of magnetic flux linkage, and I think there's one magnetic flux density.
Magnetic flux density and magnetic field strength is the same thing. Okay. Density means number of lines that basically are there, okay, in a particular volume that you're looking at or area, okay. But that has to be like perpendicular to it, and obviously this would be the model definition. For magnetic flux linkage, they generally do not ask that. I have never seen they ask anything about linkage unless they want to use that in a particular situation. Okay, it's not a direct definition, really. Okay, so
Okay, sir.
then it shows you 8 turns, and there's 12 centimeter side. This is a square, I think, right? Yeah. And then uniform magnetic field, that's into the page. Pretty good. And then they've given you the flux density of magnetic field varies. Okay, fair enough. Determine the magnetic flux linkage inside. Now we want to find the linkage. So we have to, magnetic flux linkage is basically BA times N. Do you guys understand this? So then magnetic flux, we don't know if we have that. Do we have that? Yeah, it's here. It's 400 when in 0.6 seconds, right? So we're going to use this maximum, right? So we're going to use 400, and I don't think it was milli, right? So we're going to multiply it by 10 raised to power minus 3. Area, we need to calculate it ourselves, because if this is 0.2, then 112. So it's 0.12, and this is also 0.12, which makes it 0.12 times 0.12. This would be area, and the number of turns were 8. Okay, I read off. So I don't know what the answer is. Wait. So it should be 0.046. Okay, and unit as well. So magnetic flux linkage is in Webers. So you have to write Webers. Okay, is it clear, everyone? Then is constant. Now we need to understand that the gradient is basically the EMF. Okay, so we're going to say that it's basically has a constant gradient. That's why this is a straight line, right? And then it says calculate the magnitude. So just find the gradient. That's it. So what to do? You have this, basically you had no flux here, 0, and then you have the flux linkage here as 0. I think 0.046. 0.046, and EMF is basically given, it's proportional to change in magnetic flux linkage divided by time. So the magnetic flux linkage is 0.046 minus 0, that's the gradient, and the change in time was 0.60, I think. Wait, 0.60, yes. So what you get then? 0.080, like that. Okay, so you can write that. Also, if you want to write it like more precisely, even if you write it this answer as 0.0767, that's also correct. Maybe 77, that's also correct. Okay. Then it says in procedure B is repeated, but this time the terminals of the coils are connected together. State and explain the effect of coil of connecting terminals together during the change in magnetic flux. What does he mean really? The procedure is repeated, but this time terminals of coil are connected together. Oh, here. Okay. If the terminals are connected together, what difference will it make? Like now, what happens really? Repeated state explain the effect on coil of the connecting terminals. If the terminals are connected together, that means the current will flow. Okay. And eddy currents would produce then. Okay, fine. So I would say that when there is going to be a change in flux, so current will be induced. For 3 marks, I got to write this, right? So that would be my first point. Second point should be that it would cause energy to be dissipated in the coil. All right, what kind of energy in the coil? And that's because of the resistance. All right. And the third point I would read is that this energy causes heating of coil, so temperature will rise. So I think I should write this. Is it clear, everyone? Please check your answer. If you have a different answer, let me know.
Sir, I sent my answer. Could you please check it?
Hasan Adik, how come you're in A2? I thought you were in AS still.
Assalamu alaikum.
The coil starts to rotate, but that's possible. There will be a force on it, that's true. But I don't know if it's going to rotate. I don't think so it's going to rotate. Because
So the mark scheme doesn't have that part, so I know that is wrong. It's the second line. So like, I just want to make sure if that is right, the wording.
what you've what you've sent me, it says when there's a rate of change of magnetic flux, EMF is induced in the coil, correct? This induces current, produces own magnetic field, correct? So this will cause a force, and the force direction has to be calculated then, right? So I think, Hassan Atik, in my opinion, right? Either it's basically if the current is going like this, right, towards the terminals, okay?
Yes, sir.
So then, according to the rule, it should like force should be here, according to my hand. Like it would twitch. It would twitch. Like it will go like this, I think. Do you understand?
Yes.
Yeah. So probably they would write it would twitch or the force is perpendicular or something like that. So you can write that as well. All right.
Why will it be forced
So 1
inward?
mark, 2 marks, or how much?
I think that you get like 2 marks, no more than that.
Okay, sir, thank you.
Okay, yes, Kartika.
So why will this be forced inwards?
Why would this be forced? Because of the left hand rule, Kartika.
Oh, okay.
Just use Fleming's left hand rule, right? So you have index finger towards the screen. Down, you will have the middle finger, your thumb will force here. So the current is going like this, right? It's going towards the terminals, right? Like this. So it has to be upwards, and then it will be like this. It will be like this. It will be like this. Okay, so it will be like this. So it will like just go like this. Okay.
Okay,
You-
sir, got it.
Okay. So then it says state what is meant by photon. And okay, photon, not a big deal. Photon is a packet of energy. So you write that for 1 mark, and the second part of EM radiation. Then you're gonna write this
So we can
one.
also say quantum, right?
Yeah, quantum in fact packet is the same thing. Okay. Quantum is a good word, by the way. You should use that. State the name of this phenomenon. This is obviously photoelectric effect. Okay. Up till now, I don't feel any difficulty in this paper, except for that question that had 6 marks. Lost if I'd gotten wrong. Describe 3 conclusions that can be drawn from the graph. Conclusion may be qualitative or quantitative. Oh, very nice. So first of all, from this graph, I'll see what is the frequency here, max here. It means this point, what this C is, what is this point? This is 5, 5.2, 5.4. So 5.4 into 10 is to 14 is the threshold frequency. All right, threshold frequency is equal to 5.4 times 10 is to 14 hertz. That I can read from the graph, okay? Then what else can we say? If we say, if you go here, you see E is equal to HF. So E and F must be directly proportional, which means that I'm going to write E, energy, and frequency are directly proportional. That is shown by straight line. All right. So that's good. It's not directly proportional, just write proportional. Sorry, they can't be directly proportional because it has to be kinetic energy equals to HF minus HF naught. So it has to have that. Okay. And then what else we can say? And obviously, because this whole thing, this is the work function, and that's basically photon energy. So it means that if I compare it with y equals to mx plus c, so the gradient has to be the Planck constant. Okay, so I'm going to say gradient must be Planck's constant due to E equals to kinetic energy equals to HF minus HF naught by comparison of mx plus c, like that. Anyway, then says the experiment. Yes. Yes.
I mentioned that one of my points were that um, kinetic energy of the emitting electrons does not depend on the intensity of the radiation.
Okay. Well, that's correct for the photoelectric effect, but don't you think it has nothing to do with the figure 7.1? You can't tell it from there, right? So they say drawn from the figure. So you can't really use anything else apart from looking at the figure, right? So
Okay, sir.
no credit for that as well. So then the experiment B is repeated twice, and each time you are
Sir,
making one.
excuse me, I have a question.
Yes. Yes,
The mark.
Daddy.
Oh, good Lord. Sir, the mark scheme of this question is spoken about the work function energy being 3.6 times 10 to the power of negative 19. Why though?
Because you can calculate it, no? That's fine. Because if you have this value, so you
Yeah.
can use equals to HF naught. That's work function, okay? So you can use 6.63 times 10 raised to minus 34. And then this is 5.54 times 10 raised to power 14. You can do that. You can find the value, whatever they've given. Okay, that's fine.
Right. Okay then.
Okay, then it says state one reason how the graph would compare with. So they say an experiment is repeated twice each time this. So how a different metal is used by keeping the intensity I of the radiation same. If a different metal is used and the intensity is not changed, so no matter what happens, it will happen.
Is going to
Sorry.
change. The work function is going to change because a different metal has a different work function energy.
Yes, that's correct. Work function changes, but but the line will be parallel. And the reason the line is parallel because the gradient will be the same. Okay, because gradient represents Planck constant. Planck constant doesn't change, right? And then say same metal used, but electromagnetic radiation intensity 2I. If you have intensity of 2I, like Hasan Atik has just told us, intensity has nothing to do with the kinetic energy, right? So it will be the same line. Will be the same line because photon energy depends on frequency, not intensity. Is that clear?
Yeah, yes, sir.
So that's what Hasan Atik was telling us, and that's one part of the whole concept of photoelectric effect. Okay, so that's pretty easy. There's a concept.
But sir,
This one, yes.
in this case, the rate of photo emission would double, right?
Yes, rate of emission would be doubled. That's true.
Okay, sir,
Be-
thank you.
Because at 1 second, like there will be more photons available to interact with each electron, right? That's all. Anyway, so going to question 8, what is meant by nuclear binding energy? Oh, this is pretty easy. So nuclear binding energy, like there are two definitions, right? So first of all, you can write energy required to separate the uh, constituent nucleons to infinity, and also you can say energy required to form or gather all of them in a nucleus, right, from infinity. So you try that and you get the marks. Anyway, sketch the line to show the variation in nuclear number, binding energy. Oh, okay. So if this question comes, you just need to draw a line like this. Is it clear, everyone? You don't have to show the variation. It's all right. Okay. Just remember the overall shape. This section has to be fusion, so it has to be sharp curve, and this is like less sharp. Anyway, then says state the name of nuclear process. That has to be fusion, and then that's a very poor color. And explain with reference line why this reaction result in increase results in release of the energy, because we need to write that here you might see that they have smaller masses, which belongs to this section, right, somewhere. And then obviously when they go to a higher value, which is like hydrogen generally is like, hydrogen is very near to 1. Oh, crap. Hydrogen is near to this value. Deuterium would be a bit higher. And then it's going to helium, which is even higher. So this is like 2, it's going to 3. Okay. So now there will be a difference in stability, right? Because there's a difference in energy that has to be released. Okay. So we're going to write that. Smaller particles near the start have less nucleon mass number than product. Okay, so I'm going to write that for 1 mark, and for the second mark I'm going to say, so to reach helium-3, so I'm going to write helium-3, they must release the energy difference to get to higher stability. That you should be writing. All right, is it clear, everyone?
Yes, sir.
Sir, could you read out your first statement?
Smaller particles near the start have less nucleon mass number than the product. To reach helium-3, they must release the energy difference to get to higher stability. High stability means that they have two higher binding energy per nucleon. Is that clear?
Right, sir. Thank you.
Then we're going to go to the next. Is it calculate the energy of 1 mole of deuterium? Oh, okay. Well, we're going to do that. What was deuterium? This is, we want to find 1 mole of deuterium. Deuterium was 2-1, right? I think. Okay. 2-1 means 1 proton, 1 neutron. Okay. And what else we have? We have neutron, we have deuterium here. So calculate the energy release 1 mole of deuterium undergoes this. So there are like 2 deuteriums going from here to here. Right, which is interesting, huh? Very, very interesting. So then let's do this. So there are 2 deuteriums. So we're going to do 2 times 2.014102. That would be the mass of the constituents, right? And then we have to find the mass of product. The mass of product has to be this. And what else is released with this? 1 neutron, right? So we're going to add that. 3.016029 plus 1.008665. And the difference in mass when we subtract this. So let's do this. (102) 4.028204. Always take as many decimal places as you can. Okay. 3.016029 plus 1.008665, and that's going to be 4.024694. And then let's take the difference. 4.028204 minus 4.024694, and that's 0.00351. So that's in U. Okay. And now the issue with this is that there's sort of this problem. Okay, so we're going to find the difference in energy by using MC squared. So let's do that. we want to energy in 1 mole. This is a problem. Let's see what we do with this 5-mark question. Oh my God. So 0.00351, and you're going to convert it to kgs by multiplying the value of U. If you don't know, U is 1.66 times 10 raised to minus 27. It's also written in the back. At times 3.0 times 10 raised to 8 whole square. So what you get then? Okay. So I think my calculator says 5.24. 5.244, let me write full, 394 times 10 raised to minus 13. Okay, this would be the energy change for this equation. Okay, now it says 1 mole of deuterium undergoes this reaction. 1 mole of deuterium. What does that even mean? 1 mole of deuterium has to be, this is 3, this is 2. So this is like the change in energy through total change. So we got to find how many moles of helium-3 would be there when it's formed. Interesting, huh? What is this? 2, 4, 4. Oh my God. 1 mole of deuterium into helium-3. N equals to M over MR. So that's going to equals to N over Na. That's basically 1 mole of this should go into 2 parts, like there are 2 different molecules. So it means that basically this mole has to be, the number of particles will be when I multiply this, but there are 2 of them. So basically 2 of them react and form 1. So that means I have to divide it by 2, because then it will be like half of that, because half of this and half of this will go into 1 full. That means it's going to be 6.023 times 10 raised to 20 times 10 raised to power 23, and then multiply by 1 mole, divided by, because there were 2 particles, and this will give me the total number of N's that are formed, and each N will release this much of energy. So total will be N times change in energy. So that's going to be 6.023 times 10 raised to 23 divided by 2 multiplied by 1 times 5.24394 times 10 raised to minus 13. Okay, let's do this. Times 5.24394. Okay, very big values, got to be careful. Okay, so I got the answer, and it has to be something like, why is this a positive answer? Shouldn't be a negative answer. Oh, it has to be a positive answer. Okay, so that would be 1.58 times 10 raised to power 11 joules. Okay, so this is the answer. If you guys have any questions, please let me know, please. Okay, like that.
Sir, can you explain the working after delta E?
Sir, the entire thing you did with you doing Na times 1 over 2 equals N, that part.
Yes, yes, okay. So what I'm saying is that if you look at the graph, right, what I did was I know that from the fact that if one of those deuteriums need to change to helium-3. So let's suppose helium-3 is here, right? So it says energy release when 1 mole of deuterium. It's just talking about 1 mole. So how many heliums will be formed? I need to understand this. Basically, 1 mole of deuterium means that hydrogen 2 must go to this formation, right? So how many deuteriums are going to be used for making up this? 2 deuteriums, right?
Yeah, two of them.
So it means if I say that 0.5 mole of one deuterium plus 0.5 moles of the other deuterium basically will give us that value, helium-3. Do you understand that? So it's talking about how much is 1 mole of this going to form this. So one of these are going to give 0.5 moles of this, and the other one 0.5. So total will be 1. Do you understand like that?
Right, yeah.
So what I did was I realized that I have to find moles through this. I knew I need total particles to see what is the total energy released in the reaction. So, right? So I knew that if this is like 1 mole of the total sample, then there are 2 deuteriums that are contributing to this mole, right? So I divided those two here. You get it? Like that. So you need 50% of one and 50% of the other to form like total of 1 mole of sample. That's why I did 0.5. Is it clear? Yes, Gatika, you're also clear about it now?
Sir, I'm a bit confused still.
Okay, confused still. Okay, I'll explain this way. Radhika, you need to understand this, okay? It's saying only, like, it says the energy released when 1 mole of deuterium goes. It doesn't say both the deuterium. Do you understand?
Yes, sir.
So, what I'm saying is that 50% of deuterium and then the other deuterium, also 50% of it contributes to formation of helium. Do you understand?
Okay.
So, because of one deuterium, how many particles will be going to helium? So there would be 50% of the moles, right? So if the total sample is 1, so it means 0.5 mole of this and 0.5 mole of this. You get it?
Yes, sir.
So he's talking about just one deuterium. He's not talking about both of them. That's why I did this. That I divided by 2. Okay. So then half of one deuterium will go, half number of particles will go to that. You get it?
Yes, sir. Could you scroll down, please?
Yes.
Okay, then you would multiply it with the delta E, right?
Yes, because this is just in one reaction, right?
Okay, sir. Got it.
If there were like this many particles of one deuterium, okay, this many particles in one deuterium, then basically this whole number of particles, this whole, then how much will it be? Like that, I've done it. Get it?
Understood, sir. Yeah.
Yeah. So that just remember this is one deuterium. And if you add another deuterium, then that's a different story altogether. Okay. That's fine. Okay. So this was a very, very good question. Very tough one. Okay. This is like supposed to be. Anyway, so then question 9, explain how X-rays are produced for medical. So this is the production of X-rays. So what you want to do is you say that basically you have to explain electron gun first. Electron gun is when you apply large potential difference um, between cathode and anode target area. Okay, that would give you 1 mark. Then for the second mark, you will say electrons hit target anode and jump up to higher energy levels. Okay. Then what happens is when they do jump up, they then come back to ground state and release X-ray photons. This is the production of X-rays. You can read what we've written in the notes as well. Then says state why X-ray images are taken in multiple section body compared to CT scan. During CT scan, okay. So to form a 3D image combined and processed by a computer. This is why CT scan is done. Anyway, so then they have given you this. There is a bone, there is a soft tissue, and they have given you the attenuation, okay, absorption coefficient, and then they've said uniform intensity, blah, blah, blah. It says determine the I naught intensity at point B. What is point B? Here, so it just goes through the soft tissue, right? Soft tissue is 0.89. Okay, so I'm going to use I equals to I naught E minus mu X. I need to put it here. So attenuation was 0.89 times 5.6. 0.89. Also need to check whether it's centimeter or not. It's in centimeters, so I don't need to convert this. So I just multiply 5.6. Okay. If this was in meters, then you have to convert the other thing. So exponential shift E, it's right here, minus 0.89 times 5.6. And that's going to be 0.0068. Then says point Q. So point Q is when it has this. So it goes through this and then this. So one part, second part, and third part. Okay, so we want to find this. So 1, 2, 3 we're going to do. So I equals to I naught, and then just keep on multiplying e's. So for the first part, it was minus 0.89, and the distance, if this was 2.4, and the total was 5.6. So what I'm going to do is, I'm going to do 5.6 minus 2.4, and then I'm going to divide by 2. It means this is 1.6, and that's also 1.6. So I'm going to use this. So 1.6, then I'm going to multiply E. Now bone has 3.4. Minus 3.4 multiplied by, what was that? 2.4.
2.4, sir.
And then E minus in the third section, it goes through the soft tissue again. And now just multiply every factor together and you're good to go. Minus 0.89. We already have this, so why are we doing this? We can just clearly do this 0.0068 times shift E minus 3.4 times 2.4 and then multiply by 0.0068. So it's going to be 0.000. Oh my God, I'm not writing this. Sorry. It's going to be 1.32 times 10 raised to minus 8. Okay, is that clear?
So that's not the correct answer.
What? That's not fair, Radhika.
So the correct answer is 1.7 times 10 power minus 5.
Eh? That's not fair. Wait a second. It means my calculator has not done it right then. That's not good. Okay. Let me write the whole thing. This should not go wrong. Times 1.6. Okay. Times exponential. Why is
You
it?
shouldn't have used 0.0068 because it was 5.6 as the distance.
Yes, you're right. I got it wrong. I have to do this. I have to write the full thing. You're right. That was my mistake. It was 5.6. I should have used 1.6 and 1.6 again. 3, 4, 2.4. Shift E minus 0.89. I hate this already. Okay. Yeah. This comes out to be 1.656, 1.66 times 10 raised to minus 5. That's 1.7, right? So that should be the right answer. Anyway, that says for reference to your answer whether the X-ray image in the structure has good contrast. Yes, yes, it is. It is. Because the intensity of Q is much smaller than intensity of P. So good contrast. All right, is that clear? Contrast depends on how much absorption has taken place. Okay, now, Wein's displacement law. Okay, so that's maximum wavelength, max intensity wavelength is inversely proportional to thermodynamic temperature. So it's basically lambda max is proportional to 1/T, and they've given 2 stars. We have done this question recently, so it's easy. Determine the surface temperature of B. So you do lambda 1 T1 equals to lambda 2 T2. So we're going to find the peak. So here it is. One is 0.5 times. Okay, you don't need to do times because it will cancel out anyway. So the temperature of star A, is it given? Yes, 5800. The other peak is, I think, here, which is 0.5, 0.6, 0.7, 0.65. What you get? You guys have calculated this?
Around 4,500.
4,500? Is that the correct answer?
Yes, sir.
Okay, 4,500. Pretty good. Then you say star B appears less bright than star A when viewed from Earth. And why? How physical appearance stars compares with it? So if it's less bright, because the temperature is lower as well, right? So we're gonna say star B has a larger peak wavelength. Okay. So it appears reddish color. Okay. So redder, or not reddish color, redder color. That's a better word, because obviously it would be more darker in shade. Anyway, so lines have been corrected for redshift. What is meant by redshift? Redshift is basically apparent change in wavelength that is greater in value than actual wavelength. So that means it is like shifted towards the red end. Yes.
I said that the observed wavelength is greater than the known wavelength because the star is moving away.
Moving away. Yeah, okay, that's fine. That's perfectly okay.
Okay, sir.
I mean, how cosmologists are able to determine that the light is from a distant star has undergone redshift. Oh, where did I go? What did I do? That's not fair. Wait. Okay, I was here. And yes. So how do they know? It's by this lines spectrum, okay? Spectrum observed of the light from star and compared to spectrum of same gas done within lab on Earth. Okay, so that's how you do that. Then
Sir, I sent you my answer. Could you please check it?
yes, I'll see. Yes, that's correct. That's correct. Then blank page. We can't do anything. Oh, we're done already? Only 10 questions this. Okay. Pretty good. So this would be it. And I just want to tell you a few things before we leave. Okay. Now you guys need to first of all submit your work on creating the assignment. Okay. So today was 5th. It should be 5th, right? 5th April paper. Okay, so you submit this, and tomorrow we don't have a class, but on Saturday we do. On Saturday, I don't know what is the date. Saturday is 8th. Okay, so 8th. You have to submit 8th April paper. Okay, before coming to the class, first of all. Now, I hope you guys have calculated your marks, and I don't want to ask you your marks. I'm going to go check what was the grade threshold. So it doesn't have those. So I did it for the other class as well today, June. Okay. So we did 4.3, I believe, right? If you guys scored 59 and above, that means that's a definite A, and you can scale yourself here. Okay, just scale yourself. And just remember that paper 4 is a difficult paper. And if you have lost somewhere and some marks at some point, it means that chapter needs to be redone. Okay. Is it clear, everyone? Please check it. And who got an A? Okay, that's good.
Sir,
Yes.